Good, that's how I like it. So back to circular and spherical motion. Um, Last time I defined the angular velocity vector. It's easy to imagine what this is if something's rotating in a plane. Then it's just the change in angle, the change in orientation over time. And the direction of the vector is perpendicular to the plane of motion and in the direction according to the right-hand rule. So if you have something in the plane like this, rotating this way, your fingers curl that way, and the vector is out. Okay, so it's easy to picture if you have a problem that's in the plane. If you have a spherical motion where the motion isn't confined to a plane, one thing that makes it easier to visualize the angular velocity vector is that at any given instant, the motion is confined to a plane. In the next instant, it might be in a different plane, but over some like infinitesimal time interval, this motion is happening in some plane. And then you can think of the direction of the angular velocity vector the same way, like just identify what that plane is that it's moving in at that instant. Maybe it's like this. And then according to the right-hand rule, that's the direction of the angular velocity vector. So now angular acceleration. We're going to denote that with a lowercase alpha, and it's also a vector, and it's just going to be the time derivative of the angular velocity vector, as a function of time. And I guess this is also a function of time. So that's d dt of omega. If the motion is in a plane, so that's circular motion, then the angular velocity vector and the angular acceleration vector are parallel. And if the rotation is speeding up, what do you think the orientation, the relationship is between those two directions? So they have to be parallel, but they don't have to be the same direction necessarily. They can either be in the same direction or opposite. If the rotation is speeding up, then these two have the same direction. And if it's slowing down, they have opposite directions. Either way, they're parallel. If the motion isn't in a plane, so if it isn't confined to a plane, then we're talking about general spherical motion. There's no required relationship between the angular velocity and the angular acceleration. And the directions of both can change in time. So now here are the two big equations that we're going to use. For any object in circular or spherical motion, the velocity vector is equal to the angular velocity crossed with this vector r. I'll tell you what r is in a second. And the acceleration vector is equal to alpha cross r plus omega cross quantity omega cross r. We're going to see these are going to be really important equations in this class. And largely that's, not because we're going to be looking at particles moving in circular and spherical paths on their own, but because we're going to be talking a lot about rigid bodies. And anytime you have a rigid body that's rotating about a joint, then every point on that rigid body is moving in circular or spherical motion. Okay. This r vector, this is going to be on at least one quiz, probably multiple quizzes. This r vector is the vector from center of the circle or sphere to the object. So if the thing's moving around a circular path like that, this is the object, and this is the r vector. And this, of the two of them, is going to be the more important one. This is going to come up all the time. And why is that one more important? Why is that one going to come up more often? That's right, because acceleration is the skyway between kinematics and kinetics. So no matter what you're trying to find, if you have to go between kinematics and kinetics, you need to go through acceleration. Okay. Call this one the watermelon equation because it has a lot of stuff and it's faster to say watermelon equation. But the mnemonic device I use for that is all ripe watermelons will rot. Sort of a pessimistic attitude, but yes. Are you going to propose a better mnemonic device? Yeah. Yes, R always changes in time, exactly. Yep. The other two, well, they can change in time, but sometimes they don't. But these are instant by instant equations. So when we use these, there'll be a couple of problems you'll do where you'll represent these as functions, but for the most part, you'll be calculating the acceleration at a single instant where that r is a single, represents a single instant like in that picture. Yeah. Um, because think of omega representing the plane that it's moving in now, and alpha, the angular acceleration, is doing two things. It's affecting whether it's speeding up or slowing down, and it's also affecting the change of orientation of, excuse me, in the next instant, it's going to be in some slightly different circular path, and it's that alpha that's doing that, the same way as in 2 dimensions, in just regular um, 2-dimensional kinematics. An acceleration vector has a part that's parallel to the velocity that's determining whether something's speeding up or slowing down, and a part that's perpendicular that's determining the turning, the changing direction. So it works sort of like that. What do you know about, think about from physics 1, what do you know um, about the acceleration of an object? Think circular motion. Uh, it's true for spherical motion too, but you can break up that acceleration into two parts in circular motion. What are those two parts called? Yes, centripetal and tangential. Okay. The tangential is the part that determines whether the thing's speeding up or slowing down. The centripetal is the thing that keeps it moving in a circular path. Okay. And this is the tangential acceleration. And this is the centripetal acceleration. Okay, so physics, what you did most of the time, most likely, I mean, every teaches it a little different, most likely, you just, you had an expression for the tangential acceleration that was, the magnitude of alpha times the distance from the center to the end, center to the point, and then you dealt with the directions on your own. And then this was, the centripetal acceleration was omega squared times r, and then you dealt with the directions on your own. With this expression, the vector expression, it'll do all the directions for you. Okay, but it still means the same thing. So this is always the way to calculate the acceleration of an object that's in circular or spherical motion. Okay, let's think physically about, in this example, let's think of the angular velocity going this way, and the angular acceleration going the other way. Okay. And let's think about what the directions are of the tangential and the centripetal acceleration. Um, well, what do we expect here? Thinking about this in terms of just sort of reasoning our way through the way you did in physics 1. Is this object speeding up or slowing down? And how do you know? Slowing down because omega and alpha are opposites. And it's this is moving around this way, right? So it's moving around this way, but slowing down. What's the direction of the velocity vector? It has to be tangent to the path, so it's either that way or that way. Yeah, this way. Okay. If it's slowing down, what's the direction of the tangential acceleration? The opposite direction, 180 degrees from the velocity vector. And the centripetal acceleration is always the easy one. It's always towards the center, no matter what is going on. So now let's go through these vector calculations and make sure that they give us vectors in the same direction. Okay. So we have a velocity this way. Let me draw those. So we have a velocity this way, a tangential acceleration this way, and a centripetal acceleration this way. All right, well, first we'll do the velocity. Omega cross r. So omega, this thing's rotating this way. But what does that mean for the direction of the omega vector? It's a vector. It's not a vector isn't a curvy thing. It's an arrow. So what direction is that? It follows the right-hand rule. So out of the page, right? The r vector is that way. So we're taking a cross product between a vector out of the page and a vector in that direction. That's going to go according to the right-hand rule, right? So we'll take a vector going this way, cross it with a vector going that way. And so the velocity vector is like this. So this and this rotate this way. That's like this, right? And the right-hand rule perpendicular to that is, so it's that way. Anybody have any questions about that? Yeah.
Can you explain why the angular velocity is coming out of the page?
Yeah, because so the definition of the angular velocity, well, all we care about right now is the direction. It goes according to the right-hand rule with the rotation direction. So if the thing is rotating this way, your fingers curl in that direction, and so your thumb is going out of the page. Okay. Any other questions about that? Yes.
So then, would acceleration be into the page by right-hand rule?
Yes, angular acceleration is. We just haven't gotten to that yet. We only did the velocity so far. Okay, so now we're going to do the two parts of the acceleration. We'll start with the tangential acceleration. So yeah, exactly like you said, because acceleration is going this way, the right-hand rule says into the page, right? The r vector is still this way. And so the cross product of alpha, alpha cross r is like this. And so the tangential acceleration, I didn't do that very well. So alpha is into the page. Right? R is like this. Rotate alpha towards r, and you get something like that. And the tangential acceleration is that way. And then the last one, the centripetal acceleration, we have to do two of these cross products. So first, we'll rotate. So omega is this way, r is that way. We'll take that cross product. So now we're doing the one in the parentheses, omega cross r, and we get v, right? We've already done that one, so we know we get the direction v. And now we'll cross omega, a vector that way, with v, and you get a vector pointing toward the center. So these are the same formulas that you saw in Physics 1. But now the directions are done for you. You don't have to think about the directions anymore, although it's really useful to be able to visualize this. So, I would spend a little time making sure that these directions make sense to you. Um, all right, let's do an example with numbers. So let's say a child is on a carousel, like at a playground. With a 2-meter radius. And it's rotating. So at a given instant, so remember these calculations, we're always going to do just instant by instant. So at a given instant, it's rotating counterclockwise if you're looking at it from above. With an angular speed of 2.5 radians per second. And it's slowing down at that instant with a magnitude of angular acceleration of 9.5 radians per second squared. What's the child's velocity vector? And what's the child's acceleration vector? Okay, so if we picture this from above, before we can put these in vector form, we need to choose a coordinate system. So I'm going to choose x-axis that way, y-axis that way. And the z-axis is coming out of the page. Yep. Well, yeah, if it doesn't tell you, then so sometimes you'll just get the signs as part of the problem. But in this case, the key is that the rotation is slowing down. And if it's slowing down, they have to be opposite. If it's speeding up, they have to be the same in circular motion. Okay, and this is a circular motion because this carousel can't change planes. So for part A, the velocity vector is going to be equal to omega cross r. Okay. Oh, and we need to choose where the kid is. Doesn't specify, I guess. So let's say the kid's here. Okay, this is arbitrary. If you're later you're trying to make sense out of this, try moving the kid around to different spots on there and seeing how these values change. Okay, so let's figure out what these vectors are. Omega and r. So first of all, the r vector goes, where does it start and where does it end? Starts at the center, goes to the kid. So that's the r vector. And it has a magnitude of 2. So this r vector is going to be, that's in the negative y direction. So 0, -2, 0 in SI units. And then omega is going to have a magnitude of 2.5. It says from above this is rotating counterclockwise. So what's that omega vector going to be? So it's rotating this way. So the right hand roll is like that. So your thumb's coming out. That's the direction of the positive z-axis. So 0, 0, 2.5. And the cross product of those two is it only has an x component, and it's 0 plus 5, so 5, 0, 0. Omega is radians per second, r is meters, so you end up with meters per second like you want. Okay, so does that make sense with what we know? It says that omega is that way, alpha is this way. Is 5, 0, 0 in the right direction for that point? Yeah, if it's rotating this way, the velocity vector would be in the positive x direction. And now part B, the acceleration vector is alpha cross r plus omega cross quantity omega cross r. Well, we already calculated omega cross r. That's 500. Omega, we already figured out, is 0, 0, 2.5. R is 0, -2, 0. So the only thing that we still have to figure out is alpha. This is circular motion, so we know that it's parallel to omega. And we know it's slowing down with a magnitude of, what did I say? 9.5. Okay. So if omega is in the positive z direction, alpha has to be 0, 0, -9.5. Okay, so what do you get when you cross 0, 0, 2.5 and 500? You get negative 12.5 in the y direction, minus, and then that's positive because it's y, and y is always the weird one. So 0, positive 12.5, 0. Is that the tangential or centripetal acceleration? Centripetal. So does that direction make sense where the kid is? Yep, toward the center is in the positive y direction. And now the tangential acceleration. Um, 0 minus 2 times 9.5 is 19. So that's negative 19, 0, 0. Does it make sense where the kid is that the tangential acceleration would be in the negative x direction? Yeah, he's slowing down, so it has to be opposite the velocity vector. And so altogether, the total acceleration of the kid is negative 19, 12.5, 0. And the units, we have radians per second times meters. And so that's meters per second squared, like you would expect for acceleration. I don't remember if, in D2L, I have a list of programs that are useful in this class that you can put in your TI calculators. I don't remember if this is on there, but this would be a good one to program in there. Call it watermelon or something, and just you can enter those 3 vectors. I usually do it. So here's a good calculator function. I can help you if you have a different one. I can help you program. Okay. Yeah. No, so the same idea will work in any TI calculator, but it'll take a little translating of the syntax. They change the syntax a little every time. So come talk to me if you want help translating it, but don't enter all those letters. It'll take forever. I think call it, that's good enough, watermelon. And with like the arguments, I think I do it with like A, W, R, and then those are all vectors. This A is the alpha vector, W is the omega vector, and that's the R vector. And so all you have to do is enter those 3 vectors and it'll spit out the total acceleration, which you're going to compute a million times in this class. Yes? Yeah. So if you're in circular motion, then you're probably going to line up your x and y axes in the plane that you're dealing with. So then omega and alpha would both only have a single non-zero component. But if the kid happened to be here or something, then that R vector would have 2 non-zero components. If you're in spherical motion, then all of these are in general going to have 3 non-zero components. And then it gets, with this one, it's not too hard to just do the calculation by hand. But if you have 3 non-zero components for every one of those, you'll be happy to just have a function to enter them into. Any other questions? And then I think this is the last topic in we're getting close to the last topic anyway. In what are we talking about here? Just kinematics of particles. right? So, right, kinematics of particles in non-rotating coordinate systems. So now we're going to talk about relative motion. And what we want to do is, the way we want to think about this is imagine two non-rotating coordinate systems. More used to dealing with problems where there's only one coordinate system we're using, but imagine that you have two coordinate systems taking like the same measurement. Two non-rotating coordinate systems with the same axis orientations. And when you think about a coordinate system, think about that as like a video camera that's taking measurements of something. Okay, so you have one video camera watching this thing move over here, and the other one has its axes aligned the same way, but it's over there watching the same object. Okay. What's the relationship between the observations made by those coordinate systems? Bless you. And so here's one of the coordinate systems. I'm going to call this coordinate system A. And then here's the other coordinate system. The same orientation. And I'm going to call that coordinate system B. And they're both tracking the motion of an object. And I'll call that object P. Okay. And we want to figure out the relationship between the position vectors measured by each of those two coordinate systems. So the position vector measured from A looks like this. Okay. And using the relative motion notation, I'm going to call that the position of P relative to A. How many people in here have seen that notation before? Yes, I know you did. Anyone else? Okay. Everybody? Okay. Everybody just not putting up your hands because you're like, that question demeans us all.
No.
You haven't, okay. So the idea is, what we're saying is the position of the thing in the top of the subscript, measured by the coordinate system in the bottom subscript. And we'll call that position of P relative to A. And then the position of P relative to B is this vector. And the relationship between them, notice that by vector addition, this position of P relative to A is equal to the position of P relative to B plus this vector. And what would we call this? Position of B, yep, with respect to A, relative to A. And so the relationship between these measurements is the position of P relative to A is equal to the position of P relative to B plus the position of B relative to A. You can see it really clearly as that vector addition. But as far as remembering the order, this memory device is sort of nice. The subscripts, if you have this in the proper order, have to work as fraction multiplication. Obviously, there's no mathematical reason for that. It's just how it happens to work, and it helps you organize those into the right arrangement. So what I'm saying is P over A is equal to P over B times B over A, because those B's cancel. And so if you can write it out in an arrangement where the fraction multiplication is correct, then your relative motion equation is correct. And you can take the time derivatives of this whole equation, and those give you relationships between velocity and acceleration too. And so you get that the velocity of P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. And acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. So these are the relative motion equations, these three equations. And if you ever need it, notice that for any subscripts A and B, the position of A relative to B is the opposite of the position of B relative to A. And that's true for velocity and acceleration too. So the way that we're going to use this, so the way relative motion often comes up in dynamics is, excuse me, imagine that you have like an arm connected to the ground, you know, like some kind of robotic thing, part of a machine. And then another arm connected to that. And for some reason, you need to be measuring accelerations and velocities of this point. Okay. So let's say that This lower arm has an angular velocity omega 1 and an angular acceleration alpha 1. And then the second arm has a angular velocity omega 2 and an angular acceleration alpha 2. I'm just choosing arbitrary directions. And let's make these points. We'll call this G because it's connected to the ground. And I'll call this A. And I'll call this B. And the acceleration of B relative to the ground, which is what we'd often need to calculate if we're going to use Newton's laws, if there's some important thing there and we need to know the acceleration, its acceleration. The acceleration of B relative to the ground is equal to the acceleration of B relative to the point A plus the acceleration of A relative to the ground. And the acceleration of B relative to A is just circular motion using omega 2 and alpha 2. Okay. So what we're doing is kind of assuming for a second that this point is fixed and just calculating the acceleration of B. And so we forget about these and just assume that this point is fixed and that this point is accelerating around there, right? And then we add it to the acceleration of A, and that's also circular motion. That depends on omega 1 and alpha 1. So in some complicated machine, you can calculate the acceleration of some point that's depending on all these other things using this relative motion idea. And we'll do a lot of example problems like that, and you'll end up doing a lot of homework problems like that. Anybody have any questions? Okay, that's all.